Next, let's see how to build some new combinatorial classes from old ones and then see the effect of those constructions on generating functions. So before we go on, it helps to, when we have two different combinatorial classes, we'll write their size functions like this. So this absolute value with a dot just means we would be plugging in alphas from A into this size function associated to the combinatorial class A, and we'd maybe be plugging betas into this one associated to B. Also, it helps, we'll have a fixed notation for the generating function. So the generating function for A will be written with this, I guess, Roman A, and its counting sequence will be A sub n, and similar for B. Okay, so the first construction will be pretty simple. It'll be just disjoint union, sometimes written union with a dot. So if I have two combinatorial classes that do not intersect, then I can take their disjoint union and I'll write it just with a plus. And this will be a new combinatorial class. To define a combinatorial class, you have to have a size function. So here we'll just say that the size of gamma is its size in A if it belongs to A, or its size in B if it belongs to B. So disjoint union is may seem a little strange at first because you'd have to sort of make sure that your classes are disjoint, obviously, to get this to work. So it doesn't work if they intersect because you'd have to be more careful with the size function. But then, okay, once you have this size function, well, why is it a combinatorial class? Well, you would need to make sure that all things with a given size, there's a finite number of them, but you're just getting the union of, so if I look at all things with size n, you're just getting all things with size n in A, union all things with size n in B. So it's a combinatorial class. Okay, what's the effect of this construction on generating functions? So A disjoint union B has ordinary generating function just with the sum of the power series, and you would just sum the coefficients. So this is no big deal based on what I just said about comparing the sizes, namely the number of things with size n in the disjoint union is just you sum the numbers of things in A and B separately. Okay, what's more interesting is the Cartesian product. So if I have A and B, their Cartesian product will just be ordered pairs, alpha beta, where alpha belongs to A and beta belongs to B. And the size function for the Cartesian product will be just the size of alpha plus the size of beta. And why is this a valid size function? Well, I guess we'll see in a moment how you compute it. I should point out also that if you have finitely many combinatorial classes, you can also form their n-fold Cartesian product. And in a similar way, you do the size function just by adding the sizes of the components. Okay, so what does the Cartesian product, how does that affect power series? Well, I claim that the Cartesian product has ordinary generating function given by just the product of the power series. So C of z will be the product of these. So if the coefficients are ck, these are computed using what we would just call the convolution product, or the usual way of multiplying two power series. And if you believe this computation, then you'd see that the Cartesian product is a combinatorial class, since these numbers will be all finite. So let's think about why this is true for a moment. So you just have to kind of break this up into different cases. So the set of pairs of a given size k, well, what is that? Well, let's break it up into a union where I look at the alphas of size n going where n goes from 0 to k. So if alpha is size n, then beta has to have size k minus n. But what we're computing in this part is exactly stuff of size n in A, Cartesian product stuff of size k minus n in B. And so the size of this set will be an b k minus n, and then we would just add this as n goes from 0 to k, and that exactly gives us ck. So the way you multiply power series is exactly from this formula, and so it has this correspondence to the Cartesian product of combinatorial classes. Okay, we also need some basic building blocks. And this gets a little confusing, but it's very important, even though it's sort of a simple idea. So a neutral class will be a class with one element with size 0. And maybe we'll write it with just the singleton set containing epsilon. But there could be various neutral classes that are actually disjoint. So maybe if we might need several neutral classes where we consider this neutral elements different. And so it helps to have this kind of flexibility. So usually in context, we'll just say let these things be neutral classes. We also need classes with one element with size 1, which we call an atomic class. And sometimes we'll use the notation where it just contains a dot. That's useful for maybe a graph where you have a single node, or you could write something where you have a singleton set containing A, and you just declare that the size of A by itself is 1. And so again, you may need different notations to get distinct atoms, so distinct atomic classes. But these will be helpful in building other combinatorial classes. So the neutral class, or any, I shouldn't say the neutral class, a neutral class has ordinary generating function, just the one function. So we'll write it as E of z is 1, because it has one element of size 0 and no other elements. And an atomic class has ordinary generating function, just equal to z, because it has one element of size 1. Okay, so now we'll get to examples in a moment. I'm not sure if we can say anything too interesting just with disjoint union Cartesian product and these building blocks. One of the best or most useful constructions now is a little more complicated, and it's the sequence construction. So we'll be given a combinatorial class A, and we want to form all sequences of things in A. So this will start with a neutral class, disjoint union, and then we'll have A itself plus A cross A plus A cross A cross A, and so on, disjoint union of all these different things. And you can think of this as the following set, alpha 1 through alpha L, where L gets to vary from 0 to infinity. L equals 0 is allowed, and that's just this neutral class. It's sort of the empty sequence. And then alpha 1 through alpha L have to belong to A. And we'll use the same size function that we've used for L tuples above. So the size of this sequence A1 through AL is just the sum of the sizes. And this isn't always a combinatorial class. You do need to make sure that A has no elements of size 0. At one level, that's important so that this is actually a disjoint union. But at another level, it makes you actually need it in order to ensure that there are only finitely many things of a given size. Because if I am allowed to throw in stuff of size 0, then I can get infinitely many things of a given size if I have elements of size 0. Okay, and so how does what does the sequence construction do to generating functions? Let's see, so sequence of A has ordinary generating function 1 over 1 minus A of Z, and we do need this condition here that A has no elements of size 0, which corresponds to A of 0 equals 0. And so this, we can interpret it as 1 plus A squared and so on, where this is the ordinary generating function for A plus A squared and so on. These are formal power series right now, and we'll see that when A of 0 is 0, you can actually compute this, all of the terms using a finite number of computations for each given term, I should say. So why is this true? Let's think it through. We can at least think through this part. And then the fact that it's equal to this fraction, that would sort of follow from some formal power series algebra, but we don't need to go too deep into that. When we have power series that converge, this will just follow from a geometric series. Okay, so why does this formula hold? Well, fix a k greater than or equal to 1, and let's look at all of the elements of size k. So these would be lists, or these sequences with some length L greater than or equal to 0, where the sum of the sizes equals k. And we're not allowed L equals 1 because we have k greater than or equal to 1 here. And we also have to stop at L equals k because there are no elements of size 0. So if I go beyond k, then I'll get all of these things will have size at least 1, and so I would get something bigger than k. Okay, so I have just a union from L equals 1 to k here. And now we want to think through what we're counting. Well, this for a fixed L, we're computing the number of elements of size k in the L-fold product. And so that would be the coefficient of zk in A of z to the L. And I have to do that as L goes from 1 to k, so I need the coefficient of z to the k in here, of the coefficient of z to the k in here, all the way down to a to the k, and I need it all added up. And so the zk coefficient of this will exactly be the right thing, and part of this is that the terms where I go higher won't contribute because a of 0 is 0, so when I raise this to a k plus first power, I'll only get terms with powers of z greater than k.